talk about phase diagrams, especially how to analyze the silicon-germanium phase diagrams. A phase diagram is like a map that shows how a substance like water or any other semiconductor material changes between solid, liquid, and gas phases depending on the temperature and pressure. So from the phase diagram we can determine whether a material is in solid phase or liquid phase or gas form, or it can be in mixed form as well, depending on the temperature and pressure conditions. If you heat something, it might go from solid to liquid to gas. Like for example, if we heat ice, it's gonna turn into liquid, which is water. And if we further heat water, it might turn to gas, which is steam. And actually a phase diagram actually helps you see when and how these changes happen. And we can see that for semiconductor materials as well. The lines on the phase diagram actually show the points where the substances change its state. Like for example, ice melting into water, etc. Here I demonstrate a phase diagram of silicon-germanium, an alloy used in high-speed transistors with applications in integrating analog, RF, and digital circuits onto a single chip using existing CMOS technology. So first let's talk about what is silicon-germanium. Silicon-germanium is an alloy formed by the combination of silicon and germanium, and the key benefit of silicon-germanium is its ability to achieve higher switching speeds as compared to the traditional silicon-based semiconductors, making it ideal for high-speed electronics. Now let's have an overview of the phase diagram. This phase diagram plots the relationship between temperature on the vertical axis and silicon composition on the horizontal axis in the silicon-germanium material. So as we can see over here, the composition is running from, on the x-axis, the composition is running from 0 to 100. Where 0 represents 0% germanium, which means that we are actually talking about pure germanium at this point. The 40% point actually means that we have 40% silicon and 60% germanium. Similarly, the 90% point means that we have 90% silicon and 10% germanium. Similarly, the 100% point means that we have 100% silicon and 0% germanium. And the y-axis actually shows temperature in degree Celsius. Also on the phase diagram, we also see the melting points like on the right side we have pure silicon, and the melting point of silicon is 1414 degrees C. Similarly, on the left end we have germanium, and the melting point of germanium is 938.2 degrees Celsius. Then we have the solid region, the liquid region, and the mixed region, where in the mixed region we have liquid plus solid state. In the solid region, the silicon-germanium is fully solid. The composition is fixed as a solid phase with varying proportions of silicon and germanium. Then we have the liquid plus solid region, the middle region. And actually, so in this region we have a mixture of liquid and solid silicon-germanium. As the temperature drops below this region, we are actually going into the solid region. And as we go higher above this region, the entire material converts into liquid form. Also, if you notice, we have the boundary lines between the solid region and this mixed region, and then there's a boundary line between this mixed region and the liquid region. This line over here is called the solidus line, and this line over here at the top is called the liquidus line. The liquid line is the liquid section is the upper section in which the silicon germanium is fully in the liquid phase. So the solidus line, this line over here, actually indicates that the temperature below which the alloy is going to be completely solid. Similarly, the liquidus line over here indicates the temperature above which the alloy is going to be fully liquid. Then the point is, how do we, if a particular temperature and atomic percent is given, how do we determine what percent of the material is solid and what percent is liquid? And secondly, what percent is silicon and what percent is germanium? So we actually use a line method for this purpose. Like for example, in the next slide, we are assuming that we are heating a material which initially has 40% silicon, atomic silicon. So talking about this point over here, x0, which is the initial point, we start heating the material. So this point actually means that the silicon germanium has 40% silicon and 60% germanium, and then we start heating the silicon. So as the temperature is elevated, the materials begins melting at 1070 degree C. So initially the silicon germanium at 40% content is in solid form, but at this temperature over here, corresponding to a temperature of 1070 degree C, it enters into the mixed phase. Above 1070 degree C and below this temperature is exactly 1230 degree C. So in the range of 1070 to 1230 degree C, the silicon germanium is going to be in mixed phase. Part of the material is going to be solid and part of the material is going to be liquid. So then there are two questions: how much of the material is solid and how much is liquid? And secondly, in the solid part, what percent is silicon and what percent is germanium? Similarly, in the liquid part, what percent is silicon and what percent is germanium? So we got to determine that. So as an example, we assume a temperature of 1200 degrees C. So now we have to answer these two questions. So assume a temperature of 1200 degrees C, which is exactly this point corresponding to a temperature of 1200 degrees C. And as we move along the 1200 degrees C point, we know for 40% composition, we know that we are in the mixed phase. Part of the silicon germanium material is going to be solid and part of the silicon germanium material is going to be liquid. So now we have to address two questions. One, how much is solid and how much is liquid? And secondly, in the solid part, what percent is silicon and what percent is germanium? Similarly, in the liquid form, what percent of the silicon germanium alloys is silicon and what percent of the silicon germanium material is in solid form? So in order to solve this, we actually use a tie line method. Now what is a tie line method? We draw a horizontal tie line at a specific temperature. The temperature is 1200 degrees C. So we draw this tie line which shows the coexistence of the liquid and solid phases. So we draw this tie line to the solidus line and to the liquidus line. The tie line, the purple line shows its extension to the solidus line, and similarly the green line shows its extension to the liquidus line. And then this purple line intersects the solidus line at this composition, which is approximately 67%. Yeah, 67%. Similarly, this green line intersects the liquidus line at this composition, which is how much? I would say 33%. I would say. So this is 30, you can say this 33%, and this is 67%. So it means that part of the material which is solid has 67%. In the mixed phase, we have 67% silicon and 33% germanium. So let's move on to the next slides. Like as we saw over here, read off the compositions of the liquid, which means that this is 34% silicon, and in the solid we have 67% silicon. So we can actually note down these compositions. So we look over here, 67% silicon in the solid, and then if we look at the liquid part, we have 34% silicon in the liquid part. In order to address the next question, how much is solid and how much is liquid, we are going to use some formulas. So this blue line actually shows the extension of the blue line to the atomic percent to the horizontal axis shows the initial concentration of silicon, percent of silicon, which is 40%. The extension of the purple line to the horizontal axis shows the percentage of silicon in the solid phase, represented with XS, and the extension of the green line to the horizontal axis actually determines the percentage of silicon in the liquid phase. So we know that X naught is equal to 40, XS is equal to 67%, and XL is equal to 34%. Now, once again, how much of the material is solid and how much is liquid? In order to address that question, we are going to use formulas. Percent solid is equal to X naught minus XL divided by XX minus XL. The values are also given into 100. So 18.2% of the material is solid. Similarly, for the liquid, we can use these formulas, resulting in 81.8%, or simply subtract 18.2 from 100. It means that 81.8% of the material is liquid. So once again, to summarize, we are actually in the mixed phase, and we know that part of the alloy is going to be solid, part of the alloy is going to be liquid. So 18.2% of the alloy is solid, and out of that solid material, 67% is silicon. Similarly, 81.8% of the material is liquid, and out of that 81.8%, 34% of the material is silicon. So this is how you approach this problem. You can also assume other temperature. In exam, I might give you determine how much of the material is solid and how much is liquid at 1100 degrees C at a composition of 45% initially, right? So you draw a horizontal line over here. So we come to like this point over here, right where my mouse cursor is. So I may ask you, okay, how much of the material is solid, how much is liquid? And secondly, in the solid part, what percent is silicon? And also in the liquid part, what percent is silicon? So this is how you approach this problem. Silicon germanium has various applications. We can use it in high-speed transistors because silicon germanium transistors offer faster switching speeds as compared to the traditional silicon-based transistors, making them ideal for like analog, radio frequency, and digital applications. And secondly, integration in CMOS technology. Silicon germanium can be integrated into standard CMOS processes. CMOS stands for complementary metal oxide semiconductors. And integration in CMOS technology is more challenging for other materials like gallium arsenide. So, but it can be done for silicon-germanium. So this makes silicon-germanium ideal for modern chip design without the need for specialized equipments. This phase diagram and silicon-germanium's properties make it crucial in semiconductor technology, where the alloy's integration into CMOS processes offers substantial benefits over other semiconductors. This concludes the lecture for today, and I will talk to you next time. Take care. Adios.